All right, let us begin. We have a driver in a car. This car is an open-top convertible. The driver has a tomato in their hand, and they throw the tomato directly upwards at a speed of 11 meters per second. The car is moving along a horizontal road due east at a velocity of 25 meters per second. Our question is, how far has the car moved in the time that the tomato left the person's hand and finally returned to their hand? Our immediate thought should be, what tools do we need to use in order to understand and solve this problem, to answer this question of how far the car has gone? We're given a velocity sideways or horizontally or in the x dimension. We're given a velocity of our tomato in the upwards dimension or vertical or y dimension of 11 meters per second. And then we're asked how far the car has moved. All three of these quantities are motion quantities. In other words, they relate to an object's motion. Therefore, our immediate thought should be, this is a question of kinematics. All right, one-dimensional or two-dimensional kinematics. Well, I have the car moving at a velocity of 25 meters per second, which means the tomato as well, the moment it leaves the person's hand, is also moving at 25 meters per second to the right. But the tomato is thrown upwards, a different direction, not to the right, but up, at a velocity of 11 meters per second. In other words, our tomato, here's our tomato. This is not a free body diagram. This is just an idea of what's happening with our velocities here. Our tomato is given a directly vertical velocity of 11 meters per second to start with. That's its starting velocity. And it's given a horizontal velocity of 25 meters per second to the right. There's 25 meters per second to the right. Those are the two velocity vectors we would say that are associated with the tomato. This one being the initial velocity in the x dimension. This is the initial velocity in the y dimension. Therefore, this is a kinematics in two dimensions sort of question, so I need to independently analyze what's happening in x, what's happening in y, in order to finally answer our question of how far the car has moved. It'd be helpful to understand what motion quantity we're looking for here then. The car is moving along the road or horizontally. When we see how far, we should think of displacement. Because it's horizontal displacement, then what we're really trying to find is displacement in x, which is the same as the displacement in x that the tomato undergoes in this period of time. That last point is very important for us. This question can only be answered if we know how long the tomato was in the air. How long it was in the air, multiplied by the velocity of the car, right? How the time it was in the air is the same amount of time the car was able to move along the road. At what velocity? At a velocity of v of x. We're told it's moving at a constant velocity of 25 meters per second. That should give us what the displacement of the tomato was horizontally, and the same as the displacement of the car. So here's our insight. We need to find how long was the tomato in the air, and just multiply that by the velocity of the car. Now let's begin analyzing the tomato here. We've already begun some analysis of the tomato in terms of its initial velocity vectors. It starts in the y dimension with a velocity of 11 meters per second. If, however, we take a look at the free body diagram, now I'll draw a free body diagram of our tomato. There's only one force acting our tomato if our object is undergoing projectile motion, and that is weight. In other words, the force of gravity acting on the tomato. If this is our free body diagram, then our net force in the x dimension is 0. There are no forces in the x dimension. Therefore, our acceleration in the x dimension is 0. I can go back over here to my vector, my initial velocity in x, and I can conclude that my initial velocity in x is going to be the same as my final velocity in x because there's no acceleration in the x dimension. There's no acceleration in the x dimension because there's no net force in the x dimension. The same cannot be said of forces in the y dimension. There is a force acting in the y dimension. That is the weight, or mass times gravity. That equals m times a in the y dimension. Our m's go away, divide both sides, and we find that our acceleration in the y dimension is negative 9.80 meters per second squared, or newtons per kilogram, which are actually the same units if you do a bit of analysis there. Meters per second squared and newtons per kilogram are the same units. All right, here's our acceleration in the y dimension, which means our velocity in y may start at 11 meters per second, but it's going to change immediately once it leaves the person's hand. In order to find the amount of time that the tomato is in the air, we have to analyze the y dimension. This is a question in the y dimension, right? The y dimension is what determines how long our object is in the air. The x dimension determines how far it goes horizontally, or the range. All right, so looking at the y dimension, we need to make a known and unknown t-chart here. What do we know about the motion of the object in the y dimension? And what do we not know about the motion of our object in the y dimension? Remember, our object is a tomato. Our initial velocity in y is equal to positive 11 meters per second. It's thrown upwards at 11 meters per second. We found that its acceleration in y is negative 9.80 meters per second squared. That's all we're technically given, but we know, however, that the projectile motion of an object is symmetric. So what we'll look at here is actually, if we draw a quick picture right over here, if the tomato is thrown up, it's going to be traveling forward at some velocity of 25 meters per second this entire time. The first half of this tomato's motion is symmetric to the second half. We've said before that time up is equivalent to time down. We also know that at this maximum height, the velocity of our object in the y dimension is 0. It starts at 11 meters per second, right? But every second it's traveling in the air, it slows down. It has a negative acceleration until finally it reaches 0, and now its velocity becomes negative. It goes from positive to negative. In going from positive to negative, it had to have hit 0, and it hits that at its highest point. So that's how we'll analyze the motion of this tomato. We'll say we'll only look at the first half of motion, find the time, and then multiply by 2. And that's the total amount of time that our tomato will be in the air. All right, that means that we can assume as known that the final velocity in the y dimension, if we're describing the first half of motion in y, or in the up and down, is 0 meters per second. This is helpful because now we have 3 motion quantities in the y dimension for this tomato, so we can use a kinematics equation to find a fourth unknown. The unknown we want to find, as discussed right here, was time. So this is the unknown that we want to find. We also don't know displacement in y. That would be our maximum height, but we're not asked to find that, although we could find that if we wanted to. Now we need a kinematics equation that can relate these 3 knowns in the y dimension to our time. Looking at it, my thought is the first kinematics equation, which is the final velocity in y is equal to the initial velocity in y plus the acceleration in y times the time. Okay, we have final velocity of 0 meters per second. Our initial velocity is positive 11 meters per second, plus our acceleration is negative 9.80 meters per second squared, and then times our time. If we rearrange this equation, we'd find that we have 9.80 meters per second squared times, oh, I'm sorry, that is a mistake. If we rearrange this equation, what I should have started here is rearrange this equation here. So to solve for time, I would place initial velocity with final velocity. Okay. Algebraically solve this equation and then divide by acceleration in y. That's much better. That's a much better way of solving it, at least from my perspective. I'm going to remove this and now input our quantities into here. Final velocity is 0 meters per second. Our initial velocity is positive 11 meters per second, divided by our acceleration of negative 9.80 meters per second squared. That is our time. That's the amount of time that it takes for our tomato to reach its maximum height. All we did here was input these known quantities into this kinematics equation that was solved for time. We take negative 11 divided by negative 9.80. We get a time of 1.12 seconds. 1.12 seconds that our tomato was in the air in reaching its maximum height. If I take that time and multiply by 2 times, this is just time up, right? That gives me 2.24 total seconds that our tomato was in the air. Half of that time was going up, the other half coming down. Now that I know the total time that the tomato was in the air, that whole time that the tomato was in the air, the car was also moving. Remember, the car is moving directly underneath, actually, because they both have the same horizontal velocity. The car and the tomato have the same horizontal velocity. So as this is thrown up, the car is actually moving directly underneath him, underneath the tomato. We go back to our original theory for solving this equation, solving this problem. We said, well, if we can find the time that the tomato is in the air, which we have found, 2.24 seconds, if we multiply by that time by the velocity of the car, then we would find its displacement. I'll show briefly how we came to that conclusion, of course. If we look at our definition of velocity, velocity is change in position over change in time. We can rearrange this equation. Velocity times our change in time gives us our change in position. This is what we're trying to find. We've just found the time. We know the velocity. This velocity represents our horizontal velocity. So we can take our horizontal velocity, the magnitude of which is 25 meters per second, times the time, total time in the air that we just found. That gives us our change in position. 25 times 2.24 tells us that our car moved a distance of 56 meters along the road. 56 meters along the road. Our apple also moved, or rather our tomato, also moved 56 meters to the right or towards the east in its flight in the air for 2.24 seconds. All right, let's briefly review what we just found. We have a car moving at 25 meters per second to the east. A tomato is thrown directly upwards at 11 meters per second. We're trying to find how far did the car move while the tomato was in the air. These are the two velocity vectors associated with the start of the tomato's motion, upwards at 11 meters per second, to the right at 25 meters per second, because the tomato is moving at the same velocity as the car. Our velocity in the x dimension remains constant throughout because of our analysis of our free body diagram here, in which we see only weight, or the force of gravity, is acting on the object. If we look at forces in the x dimension, there are none in the x dimension, so our acceleration is 0 in the x dimension. Therefore, we can conclude the initial and the final velocity are the same. In other words, 25 meters per second throughout. The same is not true of our forces in the y dimension. We do have a force in the y dimension that's generating some acceleration. That acceleration is our free fall acceleration of negative 9.80 meters per second squared. To find the amount of time that our tomato is in the air, we do an analysis of the motion of our object in the y dimension. That motion depends on these three quantities. We looked at the first half of the tomato's motion, knowing that it's symmetric to the second half. So if we can find the amount of time that it took for our tomato to get to the top, it takes that same amount of time for it to come back down. We found that to get to the top, it took 1.12 seconds. Multiply that time by 2, and that's our total time that our tomato was in the air. The whole time that our tomato was in the air, our car was moving at a rate of 25 meters every second. It moved 25 meters every second for a period of 2.24 seconds. So 2.24 seconds times 25 meters per second gives us a displacement of 56 meters to the east, or in the positive direction. All right, thank you.